We now discuss lectures on module 2. In module 1 we discussed about most important parameters in terms of design aspects. As we all understand, in marine structures the important environmental load which contributes to the design is essentially from the waves. Of course aerodynamic effects are important because the superstructure is having asymmetricity in its geometry and layout, therefore aerodynamic stability or wind forces are important because we have got very tall masts and cranes etc., but the projected area of these are comparatively less with respect to the submerged volume of members in the marine structures, because marine structure is essentially designed for deep draft system. Essentially we talk about flotation systems which are compliant in nature. We look for large dimension of bodies where the diameter of the structure or the member is very large, therefore it attracts lot of wave forces or current etc. So fluid structure interaction and fluid induced vibrations or wave structure interaction becomes predominantly of interest for any designer in marine structures, because it is one domain which has taken intensive path in terms of numerical, analytical and experimental research in the recent past. So let us quickly look at a very brief summary of what we understand by fluid structure interaction, how to handle them conceptually in the design. Remember, very interestingly, there is no direct application of FSI discussed in this course in this module. If you really want to look at what would be the fluid structure interaction, how to calculate the forces, we already discussed in module 1 what are the different influence of forces caused on the marine structure by environmental loads or environmental parameters. You can refer back and try to compute, because we have given you detailed equations and spectrums for waves, wind generated forces etc. on marine structures. So in this specific module we dedicate our discussion only to conceptual understanding of FSI, how fluid and structure interacts, what are the different aspects. Of course many of you may know few of these discussions, but we already have, because as an ocean engineer or as a civil engineer designing hydraulic structures you would have encountered these kind of interaction problems in your undergraduate level. For the completion sake, for the viewers, let us discuss this in detail in this course, in this module, to a great possible extent. So module 2 talks about fluid structure interaction. The contents of this module are as follows. We will talk about fluid structure interaction in this module, we will talk about flow induced vibration, and we will also essentially talk about flow through perforated cylinders. This is a very important area where people have been using perforation or perforated members in marine structures to reduce the forces on the members essentially. So this is a modern way of rehabilitating or retrofitting marine structures. You may ask a question, sir, why should I attempt to retrofit a marine structure? Marine structures have been designed for a service life of 20 years, 25 years etc., depending upon the availability of oil reserve in a specific sea state or a sea site, but you cannot make these structures to become obsolete on one night or one day, because installation, decommissioning are very expensive. So can I make use of them? So there are two ways by which these structures can be strengthened. One, reduce the payload on the structures, so relieve the structure from stresses, which is practically not possible because the machineries do operate on the same kind of loads which are exercising on the offshore platform or a marine structure. Therefore you cannot think of relieving the forces, because forces coming from the nature cannot be controlled, cannot be even computed to a higher accuracy, and forces coming on the platform or in the marine structure because of allied loads like machinery etc. cannot be controlled, because they cannot be relieved of, then the structure will not have its intended function. Then I have got to strengthen the system. How do I do? I can always adopt a perforated cover over existing member to relieve of the forces. We will talk about this in detail in the third point of discussion in this module. So in this lecture 1 we will discuss in detail about fluid structure interaction. Interestingly, majority of the marine structures do support exploration and production of oil and gas, that we all know why these structures are constructed. Other major structures are deployed essentially for harnessing wave power, because renewable energy in terms of wave energy, let us say harvesting, has become very important aspect on the recent research. So people do construct platforms where wind turbines or wave energy or wave conversion devices are installed. People also use major structures to create offshore base for naval applications, which is for strategic importance. Of course you could have seen in countries like Japan, people have started constructing floating airports, offshore airports, because land scarcity is a very major problem. Marine structures are classified either by their function or by the geometric configuration. We have already seen this in the first module. So if you look at classification of structures by configuration, based on the configuration the structures can be broadly classified as either bottom supported or floating. Bottom supported structures can further be divided as fixed or compliant. Example of fixed type you all know, jacket platforms, gravity based structures. Examples of compliant type we have understood, guide towers, articulate towers, tensional platforms, triceratops, etc. If you look at the floating type, floating structures are compliant in nature. There are again divided into two categories. One is called neutrally buoyant type, for example semi submersibles, FPSOs, monocolumn spars, these are mostly neutrally buoyant type. You have positive buoyant type, for example tensional platforms, triceratops, etc. Now these are the categories of structures available based on either form or based on other structural configuration. We will talk about fluid structure interaction, that is interaction between the members of the structures when the fluid flows across these members. Okay. FSI becomes very important for structures placed especially in the path of flowing fluid, not in stagnant water. Essentially if you look at fundamental aspect of influence of the structures in fluid flow, it alters the flow field near its vicinity, that is very important. So there is a far field disturbance, near field disturbance. So essentially we are focusing on the near field disturbance, that is what is the influence of the structure on the fluid flow characteristics in its vicinity. The degree of compliance therefore plays a very important role, because this can add complexity to the reaction it offers to the excited forces. Therefore it is important for us to understand whether FSI is applied on a fixed structure or a floating structure, because if it is a floating structure the compliancy what the structure has also alters the complexity to the reaction it offers to the excited forces. The other important aspect is, instead of having one structure in position, if you have got series of structures, series of members which are placed either in parallel or in series under close proximity, then the interactions between them will also affect the FSI in the fluid flow. So there are three different aspects here which we must focus. One, what is the structural support system, is it fixed type or a floating type, because if it is a floating type then the mechanism by which the structure generates the force internally to oppose excited force will add complexity to your interaction in its near vicinity. One. The second part is all the structures placed in series. If there are many members placed in close proximity, then the interactions between them will also affect the fluid structure interaction in the vicinity of the members. So then we have to talk about what is the optimum spacing between the members placed in series, placed in parallel, etc. So therefore in nutshell fluid structure interaction becomes interesting and sometimes it becomes vital. Now if you look at some of the idealizations which are done before we start understanding FSI, steady flow is an idealized case of fluid flow, because the fluid flow is never remaining steady, okay, it is always turbulent, it is always in a disturbed state, but steady flow it itself is an idealized state of a fluid flow. steady flow may be in the form of a current or in the form of causing a vertical shear. But in the real state, structures experience large oscillating forces in the flow direction. Okay. So, we are not anyway able to really model the FSI in its true sense, because we have do some idealization in the flow characteristics of the fluid as well as in the structural experience of the response characteristics of the system. Okay. So, when the structures are actually placed in fluid domain on the fluid flow direction, the fluid pattern is seen to be altered significantly. That is the first observation one makes. In a fluid flow, if you interfere a member of any diameter, the fluid pattern is first altered, number 1. Number 2, the restraints are developed in the fluid medium to maintain the position of the structure, because you do not want, or the structure does not want to get displaced. So, the structure offers restraint to this disturbance. So, there are two kinds of reaction you can explore in a FSI domain. One is the fluid flow is altered significantly. Second, because of this, the structure which is offering response or internal resistance to this fluid flow alteration also creates complexity to the FSI behavior. So, the forces acting on structure in the fluid medium can be classified as in two parts, as we all understand. One is a drag which acts in line with the direction of flow, other is the lift which is transverse to the direction of flow. There are two kinds of forces which generally act predominantly when a member is interfered in a fluid flow. One is a drag component which acts in line with the fluid direction or fluid flow. The second is the lift which acts in the transverse direction to the direction of flow. If you look at the drag force in general, this can be further classified as higher and smaller frequency components. Drag has got two different distinct components of frequency. One is all higher frequency components, other is lower frequency components. These components of course will be the functions of geometry of the structure, and they are also influenced by the flow conditions. If you look at the lift force, on the other hand, lift force contain essentially oscillatory components with multiple frequencies. In drag force you can distinctly identify two frequency contents, higher and smaller, whereas in lift it is a mixture. Okay. Then again, when you place a body or a member, cylindrical member essentially in a fluid flow, there are two sections of this. One is the upstream side, other is the downstream side. Upstream side is the direction where the fluid is hitting the body. Downstream side is the direction where the fluid is exiting the body. Okay. There are two different sides of looking at this scenario. On the downstream side, flow will return obviously to its unaltered condition, because the interference is caused only because of the presence of the member. That vicinity will have a validity of range. The influence of the member on the fluid flow will not remain for an infinite length. It has got certain length which is a function of the diameter of the member, okay, beyond which the influence of the member on the fluid flow can be neglected, because the fluid flow can remain unaltered in the downstream side. There are many reasons for this. The literature summarizes this as because of fluid viscosity and fluid damping. These are the two important reasons why fluid gets back to its unaltered condition in the downstream side after it leaves the body. It has got a damping phenomena present in this, and of course fluid has viscosity. Now, the region of the altered flow behind the structure is indicated in the literature as a wake region. So, wake region is nothing but the region of an altered flow which is directly behind the structure. Now, in wake regions there are many important things happening. There will be one-to-one relationship between the extent of the wake region and the restraint loads. What do you understand by restraint loads? Restraint loads are generated loads either from the complexity of the geometry of the structure, for example floating fixed, or because of the boundary conditions established by the structure with respect to the seabed, whether it is bottom supported or freely floating. So the restraint loads are essentially these kind of internal reactions which come from the structure either because of its fixity or because of its compliance. So this directly influences the extent of the wake region, how long the wake region will be extended from the member. One may wonder what is important of wake region, I will show you that in the next slide. So wake region is simply a region of an altered flow or a disturbance created because of the presence of the member. Okay. Now how long this disturbance will be created, that region, the extent of that region is governed by the restraints which are offered by the structure, either because of its compliancy or because of its boundary condition developed by the structure with respect to the seabed, maybe bottom supported, maybe compliant, maybe floating, etc. Now the fluid structure interaction interestingly in the wake region is determinant, it can be easily computed, you can have a closed form solution for the interaction of the fluid with the structure essentially in the wake region. Now one may ask me a question, sir, why we are interested in discussing only the wake region? I initially said in the previous slide, when we talk about fluid structure interaction we only bother our interest towards what is the interaction of the fluid near the vicinity of the member. So vicinity is otherwise understood in literature as the wake region. So the frequency contents of the wake region has the same as that of the restraint loads. If the restraint loads have higher frequency components, wake region shows higher frequency content or vice versa. It means there is qualitatively and quantitatively one-to-one relationship between the wake region, which we call as a disturbed region because of the presence of the member in the fluid direction or the fluid field, with that of the restraints offered. So you can always understand the restraint offered by the structure controls the interaction of the structure with the fluid. Okay, that is what we say one-to-one interaction. If you look at the fluid regimes in the uniform flow, let us say the axis of the cylinder remains normal to the flow direction, the flow direction may be horizontal, the axis of cylinder remains normal to the flow direction, the flow is considered to be having without any turbulence and boundary effects, it is a free flow domain. In that case the flow region can be divided into 4 as laminar, subcritical, supercritical and transcritical. How they are classified? They are classified depending upon the Reynolds number. Okay. If the Reynolds number varies practically from 0 to 40 or from 40 to 5 10 power 5 or as shown in the table column here, you can classify these regions as laminar, subcritical, supercritical and transcritical. Dear friends, very important to understand that there exists a very fine boundary or division between these kinds of regions, because these regions once the fluid flow starts they are continuously transiting from one to the other. Okay. So you can really cannot capture a subcritical or a supercritical region for conducting experiments. Of course it is very difficult to conduct experiments or experimental investigations in transcritical regions because the Reynolds number needs to be very high. Okay. So essentially experimental focus are done mostly on subcritical or supercritical regions. Now if you look at the distinct difference between these regions in terms of its flow condition, you will obviously notice that there is no separation of flow in the laminar region. The laminar region more or less remains undisturbed when the body is interfering with the fluid, whereas in transcritical you have got well defined vortices. So the turbulent flow will be essentially due to the randomness of the fluid viscosity, you can distinctly see these vortices in transcritical region. Of course in subcritical you can find some broken streamlines, okay, and supercritical you can see vortices but they will not be well defined. So what we can call them as ill defined vortices. Now what we are interested, as I said in the beginning, my aspect of discussing marine structures will be only on the force exerted on the system or the response given with the system back to counteract these forces. I am not interested in discussing in detail about the hydrodynamic part of the force on the system, because we are talking about marine structures, and a structural engineer I would always address this problem in terms of either the force received by the structure or the response given back by the structure to the environment. So let us talk about the effect of these regions in terms of the forces on a cylinder whose axis is kept normal the flow direction. Okay. If you look at laminar region, the drag forces are seen to occur in the direction of flow itself, whereas in subcritical region lift forces depends on the Strouhal number. You can always see very clearly there is a steady drag force with very small oscillating component of the drag force. Okay. The oscillating component of the drag force is very small, more or less the drag force remains steady in subcritical region, where Reynolds number is close to as high as 5×10⁵. Interestingly, these oscillating drag forces occur at a frequency which is practically double of the lift forces. Okay. Can clearly see two distinct difference of frequency components, one is on lift, one is on drag. You can see this, that is why we can say there are broken streamlines, whereas when you move to the supercritical region the drag force decrease very rapidly and lift and drag force seem to occur at higher frequencies. Okay. Whereas in transcritical region you can see the behavior is more or less similar to subcritical, that is why the validity of experiments what people have conducted in subcritical is extrapolated to some extent to an higher Reynolds number also, because the forces seems to be, the force on cylinder seems to be similar to that of subcritical behavior. Okay. Having understood this, let us see some focus on vertical cylinders kept in uniform flow. The vertical cylinders experience loading from the fluid flowing around it, therefore we have just now seen fluid structure interaction on the cylinders essentially is defined by the region which is controlled by a single number which you call as a Reynolds number. But there is a basic assumption here that the cylinders are infinitely long and they have a smooth and fixed ends. If you have got roughness, if you have got the ends covered, you have got a finite dimension of the cylinder, for example in case of TLP where the pontoon length or the column lengths are fixed or lesser compared to that of the water depth that you are talking about, then all these concepts what we talk about will get modified. The cylinder roughness and fluid turbulence reduces the boundary value on either side of the supercritical region, that is very important for us to understand. And of course as I said, if the length of the cylinder is finite, then a 3D aspect also to be studied in terms of the FSI. Okay, what we are talking about here is only the 2D aspect of FSI. If the cylinder has got a finite length, then 3-dimensional flow is also very important, where people do conduct experiments to understand them in the finite length of the members. The ends of the cylinder essentially will affect the drag and the lift coefficients which are computed on the members, and of course very importantly these coefficients are also location dependent of the cylinder. Where are they located? The cylinder is placed near the free surface or mid third of a water depth or closer to the boundary of the seabed, etc. And vortex shading pattern especially in supercritical and transcritical region will be significantly affected when the ends of the cylinders are covered. Then it can result in what we call reduced velocity. The velocity will get reduced. It can become proportional to the flow velocity and inversely proportional to the cylinder diameter, which is very very important. So for larger diameter the reduction can be significantly high, and shedding of vortices from the cylinder can take place at a natural frequency of the structure, which is very dangerous in terms of dynamic response behavior of the structure. Of course in certain cases capturing this kind of vortices induced vibration at the natural frequency of the member can help to generate or harness the maximum power. For example in case of let us say vortex induced vibration phenomena in wave energy devices, people design or tune the system such a way that the vibration frequencies on the vortices are captured near frequency to the natural frequency of the structure, so that the maximum energy is harnessed or captured by the device for converting it into mechanical power. So it depends upon what application looking at, then we can always design the system accordingly, but for an offshore structure where the function is not wave power generation but oil exploration, we would not like to have the shedding of vortices very close to that of the natural frequency structure, because this can result in what we call resonating response, which can increase the dynamic amplification factor of the member. Now when the vortex frequency gets aligned with the structural frequency, there is something called lock-in takes place. What is a lock-in? Lock-in actually occurs at half to 1/3 of the structural frequency, and the amplitude of this is very high. So it actually starts vibrating in a frequency at about 50% to 33% of the structural frequency. Essentially, ladies and gentlemen, please understand, resonance does not essentially occur only when the forcing frequency matches with the fundamental frequency of the structure. It can also occur at about 30 to 50% of the structural frequency. If this occurs because of vortex frequency, this is what we call as lock-in. Okay? Lock-in is a very dangerous phenomena because the amplitude is increased significantly high at these kind of frequencies. So you can always have an impact caused by a fluid induced vibration on the structure even at a frequency about half the structural frequency of vibration. This is true when the flow remains supercritical or transcritical, or at very high Reynolds number where the lift and drag forces are distinctly occurring at a different frequencies. Okay. So you have frequencies generated because of vortex shedding, which can create what we call lock-in phenomena, and there have been instances reported in the literature where members have failed because of lock-in frequencies occurring in the structures. As I said in the previous slide, we have something called reduction in velocity. Let us talk about the reduced velocity and its range as discussed by Humphreys and Walker in 1987. They have divided the flow regions into 1, 2 and 3 depending upon identifying the vortex shedding phenomena. If the vortex shedding occurs symmetric or alternate, then they divide the flow region into 1, 2 and 3 depending upon the reduction of velocity ranges from 1.7 to as high as 8.0. Now interestingly, let us look at the types of vibration caused, because we are interested as a designer how to safeguard the structure under this kind of lock-in phenomena. You will see that when the velocity is reduced to about let us say 2 or 2.3, the types of vibration is only on inline oscillation, whereas when there is a significant reduction as high as 8, predominantly it will cause transverse vibration, and therefore the failure can be more dangerous. And you will always see the inline vibrations are also seen as a frequency twice as that of this vibration. This will result in what we call figure 8 motion. So the failure will get in terms of, or the frequency distribution in terms of transverse and inline vibration will cause a resultant response of vibration which we call as a figure 8. So this will result in a very dangerous type of failure to the member under flow region. So do not be happy when the reduction velocity is as high as 8, because the moment you have reduction velocity, the amplitude may be low, maybe the velocity may be low, but the amplitude of vibration can become very high, can result in a very specific mode of vibration which can cause disaster to the members. Let us now understand the FSI in terms of deep waters. Of course, as we understand from the literature, in deep waters the flow is not uniform with depth, it varies with depth. There is a positive shear seen in this kind of behavior. the velocity of course will be greater than the near surface as you move. When the vertical cylinder is in shear flow condition, then you can always envisage what we call as a 3-dimensional flow regime will occur. So as we discussed in the last slide, we focused on wake region. Now you will see in this slide what is the effect of wake region. Under the positive shear, this is my wake region as you see in this figure, this is my cylinder, this is my flow direction as you see from here. Under the positive shear, the wake region experiences the vertical upward flow. Okay, you can see here the wake region which experience an upward flow, whereas the downward flow is induced in the stagnation line. So the member is subjected to a clear shear. Okay, the variation in stagnation pressure causes downward flow along the length of the cylinder. The flow is sheared from upstream to downstream, that is very important. The member or the structure will be subjected to what we call as a shear failure. Okay, this is downward flow on the upstream side and upward flow on the downstream side. It is a very interesting phenomena which happens on the wake region because of the flow direction in deep waters. The shear flow effect reduces pressure coefficient of course at the top of the cylinder, but of course the coefficient increases at the bottom. The coefficient also changes with the strength of shear of course present in the medium. In uniform flow, the vertical cylinder will show vortices at the same frequency over its entire length. In the shear flow, of course the frequency changes continuously. Let us now look at the horizontal cylinder in uniform flow. So far we are talking about vertical cylinders. You can quickly look at the horizontal cylinders as practical examples. You can see subsea pipelines, members of floating breakwaters, pontoons of TLPs, etc. These members are also influenced by the currents and waves. Under uniform flow field, the horizontal cylinder will generate waves near the upper boundary, which we call as a free surface. The wave resistance of course in these cases depends on Froude's number. Froude number is given by this equation, where y in this expression the depth of immersion measured from the axis of the cylinder to the free surface, and u of course is the uniform velocity present in the field. When y is very large compared to the radius of the member, maximum wave resistance will occur, and it is minimum when the Froude number is less than a number which is 0.375. Therefore the boundary effects and the end effects of the cylinder will introduce a 3D effect in the flow past cylinder of a finite length, which is true in the horizontal cylinders as well as vertical as well. Now the major difference between the horizontal and vertical cylinder is seen in the appearance of the lift force only. When the horizontal cylinder is located near the boundary, the flow will become unsymmetric. The lift force becomes function of the cylinder diameter and the distance to the boundary of the location of the cylinder. Of course horizontal cylinders will be also subjected to flow induced vibration, which we will see in the successive modules. If you look at horizontal flow cylinder in shear flow, under shear flow the velocity variation across the face of the structure will be very significant. The ratio of turbulence to the velocity variation across horizontal cylinder is higher than that of a vertical cylinder. So for increase in shear parameter, Stokholm's number increases, as we all understand, because this increase is caused in vortex heading frequency of the member. When a fixed horizontal cylinder load at the given velocity for a positive shear is much more than that of uniform flow. At a free surface, the vertical load in both positive and negative shear increases significantly in comparison to uniform flow. Therefore the dynamic vertical loads on the cylinder at the middle depth under positive and negative shear contains very high energy at very high frequency. That is why you will see generally in case of tuned mass dampers, which are attempted as one of the response control mechanism for articulate towers, you will see the maximum variation occurs near 1/3 from the MSL of the free surface. Okay, it is because of this, because you will see the dynamic vertical loads on the cylinder at middle depth close to 1/3 under positive and negative shear has higher energy at higher frequencies. So people try to attempt this as one of the important parameters to address the tuned mass control dampers in case of, for example, ATs or TLPs. Of course, near the surface as you move up there is a significant reduction. So, near the depth at about middle the variation is very severe. As you move up to the free surface there is a significant reduction in this variation. Horizontal cylinders at free surface suppress eddy shedding and the wake formation. Steady component of the vertical load increases significantly for the horizontal cylinder at the free surface. So, as you move towards the free surface horizontal cylinders attract more forces. There is something called a blockage factor which is very important in the design, which is an important aspect and outcome of a FSI. As we saw, closely spaced members interfere with an FSI. Closely spaced members connected in different orientation cause distortion in the fluid flow in its vicinity. For closely spaced members the structures become what we call dense. For dense structures the fluid flow slows down as it travels through the structure. It is very important, it becomes a cluster. When it becomes a cluster then the fluid flow or the velocity of fluid is retarded, it slows down. Velocity slowing down is always not happy, we have already seen in different regions as expressed by the researchers. It always causes frequencies at two distinct frequencies which is affecting the lift forces in the members. So, in dense structures the fluid flow slows down the velocity as it travels through the structure, which can also be harmful. This is addressed as blockage effect in the literature. This actually complicates the actual velocity field in the vicinity of the member. The blockage factor is given by this equation as you see in the slide. The load on the structure increases due to this blockage. It is very important that when the velocity reduces do not be happy, because this depends on what region you are talking about and they will induce lift forces at a different frequency which is distinctly different from that of the drag forces, which can cause complications to the structure. In fact, it increases the load on the structure. The drag force is sum for each member in the dense structure. In case of group of vertical cylinders present in the flow field, blockage factor is given by a factor as you see here, where S is the spacing of the member or center to center of the distance of the cylinder and D of course the diameter of the member. So, it is a function of the spacing or the cylinder distance and of course the diameter. So, when you talk about cluster of members in case of let us say coastal protection structures or different kinds of marine structures where we are talking about series of piles driven at a closer proximity, then please take care about the incremental in the load because of the blockage factor caused by FSI, because this is a function of spacing of the member as well as of course the diameter of the member. This lecture has the following references which I wish to acknowledge, which is available of course in open source literature. Please read these textbooks for more understanding on the points what we covered in this lecture. Interestingly, can also refer to one of my books which is available, which also speaks about these kinds of analysis and design aspects in blockage factors, which is written by myself and S.K. Bhattacharya of Department of Ocean Engineering, IIT Madras. All references are equally important, it is not because I am referring my paper here or my book here. So, my appeal to the viewers will be read these original source of reference. If you find out anything missed out in this lecture, do write to me at NPTEL IIT Madras. So, in this lecture we introduce you about FSI, what is the wake region, what is the effect of reduction in velocity, how the Reynolds number and Stokes number can influence distinct frequency of vibration, and as a structural engineer in the design of marine structures we are bothered about the response of the structure to the exertion forces or the force exerted on the structure as a component of FSI. We are not focusing more intensively on the aerodynamic aspect of FSI onto the members. So, thank you very much, we will discuss FSI continuous in the next lecture.